Hi, today we're going to talk about testing isomorphism in the CONGEST model. This is a joint work with Ruth Levy. I am Moti. So what is property testing? Probably this is one of these conferences in which I don't need to define this model, but still. So a tester with two-sided arrow for a property P and a proximity parameter epsilon is a randomized algorithm such that if G has the property P, then the algorithm outputs accept with probability at least 2/3. And if G is epsilon far from having the property P, then the algorithm outputs reject with probability at least 2/3. A tester with one-sided arrow is such that if G has the property P, then it accepts with probability 1. So this talk is about property testing in the CONGEST model. So let's have a crash course on distributed models of computation. So in these kind of models, the graph G itself is the network on which the computation takes place. There is one computer for each node of G and one communication link for each edge of G, along which messages are sent. The computation is performed by rounds, and initially each node only knows about its immediate neighbors. Afterwards, nodes exchange one message with each other in each round. In each round, nodes sends messages to its neighbors, collect the messages that are sent to it, and performs a local computation. For these models, the main complexity measure is round complexity, namely, how many rounds are required in order to perform a computational task. There are two main models. One of them is the local model, which is more classical, in which the message size is unbounded. And the model that we consider in this paper is the CONGEST model, in which message size is bounded by overflow of n, where n is the number of vertices. So what is distributed property testing then? In distributed property testing, if the graph, which is the network again, has the property P, then every node in the network should output accept. On the other hand, if G is epsilon far from having the property P, then with probability at least 1 minus 1 over poly n, at least one node should output reject. Okay, so this is the main difference. We have a network here, and the network should decide if the network itself has a property or whether it's far from having the property. So lots of papers were published on this in this area of research, and a partial list is here and more in the paper itself. And today we're going to focus on testing graph isomorphism. So what is graph isomorphism? So given two graphs, G and H, we want to test whether they're isomorphic. This means that if there is a bijection, a function that maps the vertices of G to the vertices of H such that every edge of G is mapped to an edge in H and every non-edge of G is mapped to a non-edge in H. So this was the definition of graph isomorphism. And since we're doing testing, we need to somehow come up with a matching definition for this, and to consider also this definition in the context of the CONGEST model, as we will see in a minute. So what is epsilon far from being isomorphic? So G and H are said to be epsilon far from being isomorphic if more than epsilon n square edges need to be removed or added in order to make G and H isomorphic. Okay, this is quite natural. And of course, this definition makes sense only if the graph is dense, okay, since we have this epsilon n square here. So what is a natural definition for testing graph isomorphism in the CONGEST setting? So G is again the distributed network over n nodes. An adversarially chosen node R receives H, which is, let's call it the known graph, and the proximity parameter epsilon. Now, if G and H are isomorphic, then with probability at least 2/3, all nodes in the graph should output accept. On the other hand, if G and H are epsilon far from being isomorphic, then with probability at least 2/3, at least one node should output reject. So this is in the natural definition for graph isomorphism in the CONGEST, in the distributed setting in the testing in the CONGEST model. One could think of this definition in its extreme case where we want to decide whether two graphs are isomorphic and whether they are not. So this is the decision variant. And for this variant, we have an upper bound that decides, so it's a randomized one-sided error algorithm that runs in often rounds and succeeds with high probability and decides whether G and H are isomorphic or not. We have a lower bound also for the deterministic case, and there we show that n squared rounds are needed in order to make this decision in the deterministic case. Both the upper bound and lower bound are reduced to testing equality of binary strings. More results. For the property testing variants, we have an algorithm that runs for diameter number of rounds plus polylog n factors and succeeds with high probability. We also have another algorithm that doesn't test, but does something which is very interesting. It produces an approximate isomorphism, namely it constructs a function which is almost the bijection of isomorphism. Also, this algorithm succeeds with high probability. And the last upper bound that we have is O tilde of diameter rounds for specific families of sparse graphs. Actually, this is essentially tight as we show a lower bound of omega of diameter rounds, and we show that this is actually necessary even for constant epsilon and constant error probability. And actually, this lower bound also applies even in the local model in where there is no restriction on the method length. And also if all the vertices get H as an input. And finally, it also applies for dense and sparse graphs. So let's in 2 seconds, let's get the gist of this lower bound argument, and it goes as follows. So first, the known graph H is constructed from two subgraphs, G1 and G2, which are epsilon far from each other, epsilon far from being isomorphic to one of each other, and there is a path of length O of n that connects these two. Now let's consider two possible networks, namely the unknown graphs, one that is constructed from two G1s and the other one which is constructed from two G2s. So if we assume that the algorithm is correct on a network which is G1, G2, and let's assume it was a contradiction that it uses less than some constant time the diameter rounds, then it should be wrong on both of these networks. Since if it's correct on G1, G2, then from the local view of G1, it should also say yes, everything is okay, and the same holds for here. But obviously, this network is far from being isomorphic to this, and the same thing happens also here. From now on in this talk, we are going to focus on the upper bound for the property testing variant for dense graphs, and I will give the laptop to the other author. Thank you very much.
So let's start with a naive attempt. If we have two graphs, G and H, then by making log of 1 over delta over epsilon queries to the graphs G and H, we can distinguish with probability at least 1 minus delta between the case that the Hamming distance of the graphs G and H is greater than epsilon n squared, and the case that the Hamming distance is at most epsilon over 2 times n squared. This is by a simple application of Chernow's bound. So we could go over all n factorial permutations and test if the corresponding distance between the matrices is large or not. We could use the same samples to test all the permutations. The problem with this approach is that the union bound doesn't work unless the number of samples is at least omega tilde of n. Namely, 1 over delta needs to be log of n factorial. So what we do is to follow the approach by Fisher and Matzliach, which described an algorithm in the centralized model. Their algorithm query complexity is O tilde of square root of n. A relatively straightforward adaptation of their algorithm gives O tilde of the diameter plus square root of n rounds. While our algorithm round complexity is order of the diameter plus log n over epsilon rounds. So in order to describe our algorithm, we need to define several notions. The first one is C-label. Let C be a sequence of S nodes for V. We define the C-label of V in G, which we denote by L of G, C, V, to be a S-bit string, which is defined as follows. The ith bit of the string is 1 if and only if Ci is a neighbor of V. So let's see an example where Ci is the ith vertex in the sequence C. So let's see an example. Here we have the vertex U, and since the vertex U is neighboring the vertices C1, C2, C3, and C4, we have the 4 first bits of the label on, and since it does not neighbor C5, the last bit, the 5th bit is 0. Where for V, we have that the first bit is 0 because it does not neighbor this. It is not a neighbor of C1, and so on. We say for given a proximity parameter epsilon, we say that a sequence is epsilon separating if for every pair of vertices U and V, such that the symmetric difference between their neighborhoods is the size of the symmetric difference between their neighborhoods is at least epsilon n, then U and V have different C labels. Okay, so essentially we want that if the neighborhoods of U and V is sufficiently different, then we want their C labels to be different. Fisher and Matzliach show that if the size of the sequence C is theta of log n over delta over epsilon nodes, which are chosen uniformly at random, then C is epsilon separating with probability at least 1 minus delta. We defined the notion of CD label consistent as follows. For a bijection F from the vertices of G to the vertices of H, and sequences C and D, which are sequences in G and H respectively, we say that F is CD label consistent if F maps C to D, and the C label of every vertex V in G equals the D label of F of V in H for every vertex V in G. Namely, F should map vertices in G to vertices in H such that the vertices in H such that the vertices agree on their labels. Here in this example, we see that this node has this label and it is mapped to this node, which has the same label, and the same is holds for this vertex, which is mapped to this vertex, and these vertices also agree on their label. So a useful lemma, which is essentially derived from Fisher and Matzliach, is that if G and H are isomorphic, and pi is an isomorphism between G and H, and C is epsilon separating, and F is C, pi of C label consistent. Then the distance, the Hamming distance between F of G, which is the graph G after we rename the vertices of G according to F, and H is at most epsilon n squared. Okay, so the intuition for the proof of this lemma is that nodes which have the same labels are essentially exchangeable because they are similar. So what it is implied from this lemma is that as long as we map C correctly, we can construct F which is close to an isomorphism. So what we could do now is to go over all mappings of C and test whether the corresponding F gives us a mapping such that F of G is epsilon close to H. There are only quasi-poly many options to map C to H. And now the union bound should work. The problem now is that we cannot construct F entirely. This takes at least linear time. So the question is whether we can provide random access to F. So now we describe how we construct F on the fly. For any query V to F, we map V to a random vertex U in H, such that U has identical label as V. We call that H is known, and therefore we know the labels of all the vertices in H according to every sequence. The problem is that for the sound, if we want the soundness of the for the test to hold, then F needs to be independent of the queries that are used in order to estimate distance between F of G and H. If the distributions over labels are the same in both graphs, then F, which is generated just by, as described above, namely just by mapping vertices to random vertices that agree on their labels, then we obtain that indeed F is independent of the queries that we make to it. So what Fisher and Matzliach did is that they first test whether the distributions are close. This requires omega of square root of n samples from the distributions. And the question is whether we can bypass testing distributions in the CONGEST model. And we will see that the answer is yes. So we need to define a relaxed notion of CD label consistence, which we call maximally CD label consistent, for a bijection F from the vertices of G to the vertices of H and the sequences C and D in H and in G and H respectively. We say that F is maximally CD label consistent if for every if F maps C to D, and if for every label Y such that the number of vertices that receive label Y in G and the number of vertices that receive the label Y in H is the same, then these vertices are mapped to each other. So let's see an example. Here we have the graph G and we have the graph H. So we see that for the first label, we have that all the vertices that the number of vertices that have this label is the same as the number of vertices in H that have this label, and therefore we require from F to map these vertices to these vertices. While in the case of the second label, we see that the number of vertices that receive this label in G and the number of vertices that receive this label in H is not the same, and therefore in this case we do not require anything from F. So given a node V whose label is such that the number of vertices in both graphs that have this label is the same, we can obtain F, which is independent of the queries we make to it, by mapping V uniformly at random to an unmatched node in the set of vertices that have the same label in H. Okay, so let's, for example, in this case, if we have a vertex here, then we simply map this vertex here to a graph, to a vertex here, which uniformly at random, and we obtain a F, which is maximally CD label consistent. So let's wrap everything up and see how the algorithm actually works. Then given a graph G, which is the network, and an input graph H, which is given to a node R explicitly, where R may be chosen adversarially, the algorithm outputs with high probability accept if H and G are isomorphic and reject if they are epsilon far from Riemann isomorphic. The first step is to compute a F3, which is rooted at R. Then we pick uniformly at random a sequence C of log n over theta of log n over epsilon in nodes for V. Then each node computes its C label and sends it to its neighbors. Then we pick a set of log n to the power of S over epsilon pair of nodes. These are a set of potential edges, which we denote by A. Then for each sequence, we go over all possible sequences in the graph H of S nodes. And for each such sequence, what we do is that we go over all the vertices in A. We check whether the number of vertices that have the label Y, where Y is the label of a vertex in A, is the same as the number of vertices that have the label Y in H. If this is indeed the case, then by using A, we test whether F of G is epsilon close to H, where F is a random maximally CD label consistent F. We accept if and only if some F pass the test. So the correctness of the algorithm in high level works as follows. The completeness is as follows. Assume that G and H are isomorphic and let pi denote an isomorphism between them. When testing F, which corresponds to pi of C, then with high probability this F will pass the test. For the soundness part, let's assume that G and H are epsilon far from being isomorphic. Then for any F, F of G is far from H, and with high probability it will fail the test. For the main open questions that we leave in this work is what is the complexity of testing the exact problem for randomized algorithm. Can we obtain one-sided error algorithms? Can we obtain algorithms for general graphs and not just for graphs that are dense or sparse? And what about considering other models? For example, a model in which the known graph is actually not known and we can access these graphs via queries. Thank you for listening and for your attention.